Hello, I don't know about you, but my students often ask me the question, how to use a z-table, how to use a student t-table. So in this video, I will show you how to use a z-table and how to use a t-table to calculate probabilities, quantiles, and critical values. Let's get to work.
Imagine that you have a standard normal distribution. Here is a random variable from a standard normal distribution. I will show you how to calculate probabilities, quantiles, and critical values. So let's start with probabilities. Say that you would like to calculate probabilities. In other words, you would like to calculate CDFs for a standard normal variable. So say that you would like to calculate, let's start with the probability that z is less than or equal to 1. Well, I will show it to you using a z-table. Well, you have tons of z-tables. If you understand how to use mine, well, I'm sure that you understand how to use yours. So here is a typical z-table, and it contains probabilities. So basically, what is highlighted in red, if you see the colors, well, the area on the left is what is reported in the table, in the main part of the table, the white part of the table. And here, the highlighted yellow numbers show you the number where this little lowercase z is located. So if you want to calculate the area on the left, starting a particular little z, well, you look for the particular little z here in the yellow area, and you find your probability. So concretely, if I am looking for this probability that the standard normal random variable is less than or equal to 1, concretely, if I draw here my standard normal distribution, I would like, so here is 1, and I would like the probability that is highlighted here, right? And this is the so-called CDF, right? Evaluated at 1. So using the z-table, I look for 1. Here it is, 1 in the highlighted area, 1. And this is my second decimal. My second decimal is also 0, right? So this is the number that I am looking for, 0.8413. Now, if you look at this, if you go back to the z-table, then basically what I see is that I only have positive numbers. But that's enough for me. So imagine that I'm looking for the probability that z is less than -1. In other words, the CDF evaluated at -1. So here, basically, what if I draw the situation, well, I am looking for so here is -1. I would like to have this area, right? But in my table, I have positive numbers. So I have basically the CDFs evaluated at these numbers here. So I will try to use these numbers to calculate my area here. I can, by symmetry, because the standard normal distribution is a symmetric distribution, I can report this yellow area on the right. So the two yellow areas are the same. But if I say that I hatch this area here, that corresponds to what? The hatched area corresponds to the CDF, precisely, this is what I calculated above, right? That's the CDF evaluated at 1, right? And since I want the yellow area, I want the remaining part. I know that the total is equal to 1. So this is 1 minus the CDF evaluated at 1. In other words, 1 minus 0.8413, which gives me 0.1587. Now, imagine that I would like to do something else now. Quantize. Say that I would like to calculate quantiles and not probabilities. Say that I would like to calculate, take a particular quantile, the 0.67th quantile, why not? For standard normal distribution, I still consider the situation, for now I consider standard normal random variables only, right? And concretely, if I draw this situation, quantiles, what are these quantiles? So this is still my standard normal PDF. Well, 0.67 is something so it's this value on the x-axis such that the area on the left is equal to 0.67. How to find this number, this quantile in a z-table? Well, I look for my 0.67, and how convenient. These are in increasing order of probabilities. So I look for 0.67, and here I am. Here it is, 0.67. So I report the yellow highlighted number, 0.4, second decimal is 4. So this is 0.44. Now, in my z-table, I only have numbers that are like 0. I only have specific probabilities, right? So say that I am looking for a number, for a probability that is in between two numbers. So say the 0.9th quantile. Well, in my z-table, we said that it's in increasing order of probabilities. So 0.9, 0.9. Here I am. It falls between this number and this number here, right? And these two correspond to 1.28 and 1.29. So what happens when my probability is in between two numbers? Well, I simply average. That's a common way. When you use z-tables, it's not an accurate way, but that's the only thing that we cannot, we can only approximate with the z-table. So I will average the two numbers, the two closest numbers, which gives me 285, and that's an approximate way of providing the quantile. That's all we can do with a z-table. Now, in a z-table, I only have numbers, probabilities that are greater than 0.5. How to find a quantile corresponding to a probability that is less than 0.5? Say the 0.1th quantile. What do? If I, let's draw the situation. So here I would like to find a quantile such that in this area, right, in the yellow area, I have 0.1. And I only have in my z-table numbers that are greater than 0.5, so once I am in this part of the distribution. So let's use that part. If I report again my yellow area on the right, same thing, my yellow area corresponds to something such that I have 0.1 here. Then I know that this is my if I write it with quantiles, it's my 0.9th quantile. But by symmetry, this thing I can find it in my z table, right? 0.9 will be there. And by symmetry, this thing is the negative of my 0.9 quantile. Okay? So it is the negative of the 0.9th quantile, and 0.9, if I look for 0.9, where we already actually calculated previously above here, so it will be the negative of 1.285 approximately, right? What else? Critical values. When you test hypotheses, you often look for critical values. And these are basically quantiles. You can rewrite them with quantiles. What do I mean by a critical value? Simply a value such that in the right tail I have alpha. And let's put a star on top of alpha. If we are doing regression, alpha may mean the intercept. So this can be written with quantiles, right? Above, quantiles measured areas on the left. So this can be rewritten as the quantile corresponding to the probability 1 minus alpha star, right? So this is what it is. If you look for right areas in the right tail, then you can write it this way. So for example, if you look for the 2.5% critical value, then this corresponds to this thing, right, with our above rule, and 0.975, where is it? 0.975, it's here, right? How convenient, it's precisely there in the table. It corresponds to 1.9 and second decimal 6, right? Now, this is enough for the standard normal distribution. Let's move to a student t distribution. So imagine that we now have a random variable from a student t distribution with a particular degree of freedom. I will start this time with the critical values just because often it's the critical values that are reported in a t table, in a student t table. Just because you typically want to test hypotheses with a student t distribution. So here it is. Once again, there are tons of student t tables in nature. If you understand how to use mine, you will be able to use other type of t tables. So here is mine. You have what is different from a z table is that you have one additional basically parameter, a degree of freedom, right? That is reported and is reported here in this column where it's written df. Now, a student t distribution, recall that a student t distribution looks like a standard normal distribution, right? But it has fatter tails than a normal. So typically a normal would look like this. It has thinner tails, but when, so say that with blue I draw the standard normal distribution, and with black I have the student t, and the smaller k, the fatter the tail, and when k goes to infinity, well, the student t converges to a standard normal distribution. So yes, it's more and more like the standard normal distribution. So now, since we have several degrees of freedom, I will need a lot of space in order to report the same information in a Z table. It's impossible to report in a T table all the information we have in a Z table, right? Because here we do not have this extra parameter, this df. And here, basically, in one row, I report the most useful information for each distribution, because for each degree of freedom, I have actually a different distribution. And what I report, what is typically reported in a T table, are critical values. In other words, say that I'm looking for the critical value for 5 degrees of freedom. So I have a student T with 5 degrees of freedom, and I would like the which critical value corresponding to 2.5%. In other words, I would like, what am I looking for? I am looking for a value such that we said that for critical values, I basically want to have the right tail to be equal to 3.5%. And so this is the critical value, T5, 0.025. And in a T table, I first select my degree of freedom, so 5. I look at row 5, and I look for the column where it is written 2.5%, but where it's written one tail. We have two rows, not in all T tables, but in this table, in this T table, we have two rows. The first one is written one tail, and the second one is written two tail. Basically, what it means is that you can check the area in one tail or in the area contained in two tails. Now, since I drew it like this, I only look at one tail, right? So I go back to my T table, so I select this one tail row, and I look for 2.5%. Here it is, 2.5%. And I go down to the row 5, so this is the number that I'm looking for, 2.571. Now, as you could guess, well, we cannot report all the degrees of freedom. So say that I am looking for, say that I have a distribution with 34 degrees of freedom, which is not reported in the T table. So say that I look for the critical value for a student T with 34 degrees of freedom, and say that I would like 0.25 as probability in the tail, area in the tail. Then I go back to my T table. 34 is not there, right? So there are two methods actually, which you cannot do an exact calculation anyway with the T table. So any critical value calculation is just an approximation. So the two typical ways of doing this are the following. First approach is to average the two closest values, so 30 and 40. So I look for which column. We said 0.25. 0.25 is here. 0.25. I go down, and I have these two values, right? The two closest values are this and this, right? So just to summarize, right? I look this time for 0.25. So this is my critical value such that I have 25% in the right tail. So we said that we averaged the two closest values, which were 0.683 and 0.681, right? That's one way of doing it. yes, which is 0.682. Or alternatively, because anyway it's just an approximation, you can also take, which is quicker, it's much quicker to simply take the closest value. So 34, closest degree of freedom is 30. So it's simply the first number. Here you go, 0.683. Or take the closest degree of freedom, which would provide us the approximation 0.683, right? Now, this is for the critical values. Now, imagine that you would like to calculate quantiles. Well, say that I would like to calculate the quantile the 2.5% quantile for a student T with 5 degrees of freedom. In other words, I would like to have quantiles measure the left tail, so I am looking for a value. This is the student T with 5 degrees of freedom. A value such that in the left tail I have 2.5%, right? And this I can rewrite with critical values, because in a t-table what I have are critical values anyway, right? So let's rewrite it with a critical value. Critical value means that I look for the right tail. But we said that we cannot find critical values such that the area is greater than 50%, which is what I would have here. So I will first report it in the right tail. Here it is, right? This corresponds to 2.5% as area. And this would be the critical value, right? This would be the critical value, the 2.5% critical value for this distribution, right? And by symmetry, this is just the negative of this critical value, right? And this I will find in my t-table, right? I go to my t-table, 5 degree of freedom is here. And we said that 2.5% in the right tail, so one tail, 2.5 is here. I go down 5, 2.571, right? This one, 2.571. Now, let's also look at probabilities. This is the most difficult thing to do with the t-table, to calculate probabilities for a student T. Say that you would like to have an information about the p-value of a test. Well, it's more difficult. So say that, let's take an example in which we have a student T, a random variable from a student T with 5 degrees of freedom. And I would like to say something about the probability that T is less than 1. Well, I will not be able to say it for sure. Even approximation is tough, actually, with the t-table. Well, the idea is the following. So this is my student T distribution. And I would like the probability, right? I would like the probability of the yellow highlighted area, right? Now the only problem is that I don't have probabilities in a t-table, right? I have critical values, but I have information here. These are probabilities, right? Measuring the right tail. So I will try to survive with this. What I can say is that if I go back to my t-table, for 5 degrees of freedom, I know that I have numbers that are close to 1, right? I have 0.92 and I have 1.156. These are the two numbers that I have in my t-table. And the corresponding right areas are 0.20 and 0.15. What do these things mean? If I report now here, I know that, so what were the numbers? So for 15%, I had 1.156. I know that, let's highlight it with another color. I know that this corresponds to 0.15. And I also know that 0.92 corresponds to 20% in the right tail. 0.92, which is somewhere here. 0.92. Right? This corresponds to, and here it's tough to, but I will highlight it like this. All this hatched area corresponds to 0.2. So basically, the one that I'm looking for, this yellow area, is in between this 20 in the right tail and 15 in the right tail. But I look for the left tail, right? So concretely, I can say that this thing will be in between what and what. So here for 0.2, I know that in the left tail here, I have 80%. So it will be between 80%, so I can write 0.8. And this blue area corresponds to 85% in the left tail, 0.85. So this is all the information I can say about probability for a student t-distributed random variable. All right. So thank you very much for watching. If you want to have the same table, Z table and T tables that I am using, you can go to my website, which is here. So here is the link to my website. Thank you for watching.